The other one that I wanted to talk about was this one here, was the gravitational wave astronomy, opening up new windows in the universe. And it was given by Martin Hendry, who was, in Glasgow in Scotland. And he gave a marvelous talk. He sent me his slides for the talk, and it was also nice to hear a Scottish accent, was right at the beginning as well, so I could get accustomed to it. So it was relatively thick, so. Anyway, so we're just a little bit past the 100-year anniversary of the theory of general relativity from Einstein, and many of you probably heard, and I reported on this in a previous 60 Minutes in Space, that the first gravitational waves were detected just shortly after that period. I'm going to talk a little bit about that detection again as well as another one. But this was a meeting about some of the new things that are going to be coming on board, some of the technologies associated with making this kind of measurement. So this particular instrument and the way we detect gravitational waves is we have a couple of these detectors. This one's in Hanford, Washington, and this one's in Livingston, Louisiana. The way these things are constructed is there's two arms here of this detector here, and you see them over here, and basically there's a laser that hits a mirror, goes out, hit another mirror, and hits another mirror here, and I'm going to show you a little video here of how this actually works. But what it's trying to measure is the differences in distances between these two legs as a gravitational wave actually comes on by. And so we'll start this off. So here's the laser beam that comes in, they come back together, and then here's the detector. And so when a gravitational wave comes in, it does that to the signal there, so as it comes on by. So I'm going to do this a little bit slower motion, showing the wave motion of the light. It goes off to the different mirrors there, and when it comes back together, those two waves are selected to basically interfere with one another and cancel one another out. And so back over here, they're hitting this detector there. And in general, if these things are not moving, you get no signal right there. But if they start to move, and this is the way gravity's waves work, as one gets longer, the other one gets shorter, the distances change, and you can see that those two beams don't interfere exactly, and the light goes up and down there. So that is the basic detection signal that one measures. The thing is, this amount of motion is extremely small, and so it's very, very impressive that these detectors can even measure this phenomenon. So, in fact, so we measure that phenomenon by something they call a strain amplitude, which is the change in the length divided by the length. So in this case, the LIGO interferometer arm is about 4 kilometers long. So that change divided by that is 1 part in 10 to the 21 power. That's 0.2001 there, okay? So that's a very, very small fraction. It's amazing that they can even make that measurement. And there are, like I said, there are 2 of them over here in Washington and Louisiana. The thing that has happened, and they have a certain sensitivity in their ability to detect this strain here. So those are those numbers. I said they better than 10 and minus 21. Here are the sensitivities of those 2 different detectors, and you can see their best sensitivity is right here at the base of this, and it determines the kind of frequency that they would see in this kind of event. And I should back up here too. So the kind of events that we think we can actually detect are some of these really violent things where, things that give off gravity waves are things where you have mass that's moving. So like if I move my hand back and forth like this, I'm creating some gravity waves, and they are so small we have no chance to ever measure that kind of gravity wave. But in the case of these massive objects like 2 coalescing black holes, you can see those things actually put out gravity waves. And I'll show a couple cool movies on that shortly here. And it can see some other less violent things like pulsars, which are a rotating neutron star if it has like a bulge on it or something like that, because then the mass is not symmetrical and it actually produces that kind of same shaking kind of thing that can put out gravity waves. So we have hope to measure, a lot of these objects. Now, the reason that the LIGO was able to make a detection back in November was it improved its capability. So LIGO, when it first got up and operational, was this green curve right there, and you can see it only got down to about 10 to the minus 23. Now it's getting lower here, and with the advanced LIGO, and there's plans to make it even lower on here, and almost another factor 10 in sensitivity. One of the cool things that Martin talked about in terms of how they achieved that kind of sensitivity is you've got these two mirrors that you're trying to figure are mass objects there that you're trying to figure out how they might be actually moving. Well, you don't want them to be vibrating by, you know, a truck going by outside or someone stamping on the floor and things like that. So you have to isolate these so it's in a very, very quiet environment. So one of the things they did is this kind of this 4-quadra suspension technique here. So here's your test mass back here, hanging on cables here, hanging on cables here, hanging cables here. So that is totally vibrationally isolated. It's one of the quietest spots you can ever actually go. And so here's the pictures of that apparatus there. The other thing that they were doing that the Scottish group was involved with is actually replacing the steel suspension wires used to hold these up with actually the silicon fiber so that you get less expansion due to temperature differences and such. So pretty cool technology. They got this advanced LIGO, they dedicated it in May 2015, and it was supposed to be doing their first observing run on September 18th, and luckily they got that going earlier because it was September 14th that they actually made their first detection. And I talked more in detail at a previous 60 Minutes in Space on that, so I mean, I'll mention a little bit more, but these are the kind of signals that they actually measure. And basically this is measuring this strain amplitude as it's moving up and down here, and you can see it gets closer and closer here, and this is the coalescence, in this case, of two black holes there. This is the measurement at Hanford, this is the one in Louisiana here, and you can see the signals look very, very close to one another. Now, they didn't build two detectors because they got to buy one, get one free deal. It was because if you have two of them, you can confirm that indeed you're looking at something that's happening out there in space, so they're not, and also the time delay between those two give you an indication of where it is that that particular event happened on the sky. And so I'm going to show you later how these ones actually sound, because there was a new detection that I want to talk about, but they produced these little graphs here and everything, and there's been a lot of things going on in the astronomy community about these detections. So here is actually a simulation. I like the way they do this here. So this happens in, there's 0.65 seconds there, and you'll see down here that's where it's joined. So this is in a half of a second of time, showing in this case the two black holes that coalesced there. They're showing down here kind of the curvature of space-time below here. And you can see how short of time this all happened. This is something that happened a billion light years away. Took millions of years, to, if not billions of years, to spiral down to this one instant, and it happened very, very quickly. And you can see that the last part of it speeds up very, very quickly. They'll freeze it right at this point or slow it down. You can see the time frame there. And at a point, they could then coalesce at that point, freeze the movie right there, and then you have a little bit more going on in the signal there, and then things get totally still after that as it settles in there. And these are the gravity waves that are moving on out. So it's a very interesting signature. You see this, and you can actually hear that. And so I'll play a little later on how that tone sounds. So anyway, this is like opened up this huge new, astrophysical toolbox for astronomers, that we're going to be able to learn many more things about these objects that we really don't have any ability to do. These are, the first detection of gravity waves, but they also are telling us about these black holes that exist. And so one of the things that was kind of amazing about this particular one, so this is kind of the things that it can actually tell. One of the things it can tell is how far the thing happened. So in this case, it happened about 400 megaparsecs. It's about 1 billion light years away. It also it's kind of coupled to the orbital inclination. In other words, how is that orbit compared to our line of sight? A thing that was interesting to me that I didn't realize is it also detects whether the black holes were spinning at all. And in this first one, it was consistent with that they weren't spinning very much. It tells you what the various masses of them are. In this case, the mass of this one was about 30, this one was about 35 solar masses. This is before they spiral down. And also tells you what the final mass is. In this case, it was about 62 solar masses. That meant that three times the mass of the sun was converted into energy in that small fraction of time, which is the amount of energy that the entire universe puts out. The visible universe puts out in that amount of time. In fact, it's more than that. I can't remember the exact number. So it's an incredible amount of energy that's being put out just in gravity waves. So it's also a way that we can test general relativity. And so I like the way Martin put it. So, you know, Einstein is not wrong yet. No, but I mean, every little test, if we put kind of upper limits where it still fits general relativity. So it continues to fit. We have not shown that general relativity is not the right theory that describes gravity yet. In terms of the size of this black hole, here is how big it is compared to Great Britain. That's where the event horizon would be. That would be the point in which light cannot escape that black hole once it was formed. So this is the 62 solar mass black hole there. And it also, I told you that we have two sensors because it can tell where it is on the sky. And I'll get back to this just a little bit later. But is a kind of a big strip where we think it happened. But one of the things we want to ultimately do is to figure out, is there some other visual signature? Did something happen with light, we call electromagnetic follow-up here, in other words, light, that happened in those regions? And there were some potential candidates. Nothing is shown that it happened, but it's a huge amount of space that one would have to cover. So anyway, the thing that happened in June of this is they confirmed a second detection of two actually merging black hole systems. So that was in the news, and wanted to show you the same kind of data for this one. And if you look at that data, it's not very clear that you can see that like you did with the 30 and 35 solar mass ones there. But they were able to develop these techniques called match filtering. They were able to detect this, within hours after the detection, and it's in that signal. And ultimately, you can see, some structures of that signal. But this was a much smaller system. It was one where a 14 solar mass black hole merged with an 8 solar mass black hole. And the one thing about it is the frequency was a lot higher on that. So anyway, the filtering matching did that. Oh, so here's how they actually sound, sorry. And here's the earlier one, it's a lower pitch. They're gonna do it one more time, and then they're going to, it's the natural pitch. And now I'm going to increase this. So you can actually hear that in the data when, so you don't hear, you're not really hearing the black hole, but the frequencies in which they're doing that is at the same as the human hears that, so that you can actually convert that into a sound. And so it's really cool that we're listening out there to the universe. So what I was going to say on this one. Oh, so this one spent almost 1 second in band. So in other words, they got to see a lot of these oscillations before it merged. So it's in a better frequency. So even though the signal's not as strong because they're smaller black holes, they got to observe it longer. So I'm going to, and the other thing that they detected on this one is that one of them was definitely spinning. So there's pretty high probability it's in this area here. What this 30% and 60% means, and it's somewhere like 45% is here is the center of that region right there. That meant that that black hole was spinning at 45% of the maximum that it can actually spin. So very, very rapid. So this is the first detection ever of a spinning black hole. So there's going to be a lot of parameters that they get out of that. Here's kind of showing the sensitivity of the detector and the events that one were able to detect. So here's that first one that happened in September here. Here's the one that happened here in December, just the day after Christmas there. And there's this other green one in here, which was another detection, but it's not a confirmed detection. It won't be a confirmed detection, but it's close enough that they've been including it in these other things. Okay, and here is the model of that. And so you can see that they got many, many more orbits of that particular one. So there's the 14 and there's the 8 solar mass one there that are involved. They're working on the way of actually presenting this, but I really love this little graph at the end here so you can see how it changes. It's an amazing signal. That's why it makes that chirp. It gets to this very high frequency at the end, and then it's just calm. It's just kind of an amazing thing. You have this incredible violent collision, and then the waters are totally still after that. And you can see when it goes to that last part of it, as I zoom in a little bit closer here, it just happens so fast. And those gravity waves that are moving out, those are the ones that ultimately, a billion light years away, we are detecting here on Earth. It's just amazing that we can actually do that. And just these few detections have added a lot to the black holes that we know of known mass. So here are kind of these lower mass ones that are about 10 times the mass of our sun. Over here, done by X-ray studies where you actually see the companion, the black hole with some other star going about it. It's collecting light from that, or collecting matter from that other star as it's spiraling in, it's giving off X-rays, and so we can get the parameters to actually measure the mass of that. So we've added quite a bit to that inventory, and one of the big surprises is how massive these objects that we have found. And so it's very, very exciting because there are going to be more of these. It's now starting to put some limits on how many we expect to find out there. The error bars are pretty big right now because we've only detected 2, but we're, when this gets turned back on again, it's currently off. It's going to be going on to the next run and stuff. We're going to be detecting a lot of these objects, and as they reduce the noise and improve the sensitivity, we're going to be hearing a lot about this field. So it's very exciting. And the other thing is here's where, for the December one and the September one, where they might have been located on the sky. We need to do a little bit better job than that, and there are new interferometers that are coming online. This advanced Virgo one is supposed to be on in a year, I think, here, and then this one has been approved, so there's going to be this one in India, and there's another one over here, and I can't remember what the status is on that, but ultimately what that will do is when they bring the Virgo system on there, all of a sudden the error bars in different parts of the sky are going to be like this, much smaller, and then when they add the one in India, you're going to be able to localize more where that event occurred, and therefore know where to point your telescopes to see if anything happened in the electromagnetic spectrum.